Okay. Good afternoon, everyone. Welcome to our fifth RICE ECE Wireless Distinguished Series seminar. So before we start, I guess like always, I'm going to give a little bit of logistical explanation on how we're going to conduct this for the people who are joining us for the first time. So if you have any questions, please leave your questions in the Q&A section below. And then mostly, I guess we're going to read the questions after the talk, and our guest will actually answer them. With that, it is my great pleasure to introduce our distinguished speaker today, Professor Ness Shroff from Ohio State University. Professor Shroff is currently the Ohio Eminent Scholar Endowed Chair in Networking and Communications in both EC and CS departments and at OSU. Professor Shroff's research areas span communications, networking, machine learning, cloud and data analytics, and security, with his papers receiving more than 20,000 citations. He has been noted as a highly cited researcher by Thomson Reuters in 2014 and 15, and listed on the world's most influential scientific minds. He has also received the IEEE Infocom Achievement Award for seminal contributions to scheduling and resource allocation in wireless networks, along with many other best paper awards. Dr. Shroff was previously an ECE professor at Purdue and a visiting chair professor at Tsinghua University in China, and currently holds guest chair professor positions at Jiaotong University in Shanghai and IIT Bombay in Mumbai. He currently serves as the steering committee chair for ACM Mobihawk and editor-in-chief of IEEE ACM Transactions and Networking. So with that, I would like to welcome our distinguished guest to this virtual seminar today. Professor Shroff, the floor is yours.
Thank you so much. It's a real pleasure to be here. So Edward, Ashu, and I have been talking for many years to have exchange visits between our institutions, but it's been a long time since I've visited RICE. So it's really fantastic to do this even remotely. So thank you again for the invitation. What I'm going to do today is I'm going to talk about a relatively old problem in the area of resource allocation and control that has been around for over 2 decades. This is the problem of network utility maximization. And a few years ago, DARPA sort of asked me some questions regarding some of the work that was going on and how it was needed in military networks. So it was some of this research was initially motivated by that, but really because of the emergence of cloud computing and large-scale data networks as well, I believe it's important to take a fresh look at this problem. I should mention that this work is being led by one of my ex-students, Sinong Wang, who received his PhD a couple of years ago. A brilliant student who unfortunately was stolen from academia by, the riches of Facebook. So, all right, so here is the outline of the talk. I will let you read it, but essentially I will begin with an introduction that motivates, some of the reasons why we want to study this problem, some of the issues with the state of the art, and then I'll talk about our new approach. I'll very quickly outline the key results. And then we'll spend some time, which might be interesting to some of you, to sort of look into some more details, right? So looking under the hood, understanding how the algorithm was designed. And if there is time, I will talk about some of the proof techniques that we used, and at least give you some kind of high-level understanding of the challenges in the proofs. And then we'll summarize and we'll talk about many open questions that remain. All right, so let's begin. As all of you know, big data has become really, the flavor of the day, week, year, decade, and for good reason. So according to this particular website, since the dawn of civilization in 2003, it says that humans generated roughly 5 exabytes of data. And since 2003 until 2015, it turns out that humans generated that almost every other day. And as you can imagine, since 2015, this has grown enormously already, exacerbated by a variety of machine learning and AI types of applications, which has also led to the development of massive data center networks, which have become large, ubiquitous. So here is an example of how many data centers Amazon has, etc. So because of this emergence of data and the need to manage this large volume of data, there are some significant new challenges that we face in the design of communication networks. And let me sort of go through some of these challenges. So the first one is the issue of latency, and especially needing to have very low latency. So why is latency important? I'll give you a couple of examples. The first one is electronic commerce, which has a huge market just in the US, and as you can imagine, in 2020, this number is going to get substantially dwarfed. So apparently, Amazon did a study a while back and found that every 100 milliseconds of latency resulted in 1% of sales, right? And so it's critical that websites be designed, protocols be designed to sort of handle this latency issue. Another a big industry which just continues to grow is online gaming, where people have found that if the delay grows by a factor of 2, the user playing time reduces substantially. Right? So this is another very mature industry where delay is critically important, and there are many others, the stock market, etc. The second big issue is that the infrastructure is used in a haphazard manner. So there was a paper in 2015 which showed that the Ethernet in Facebook had a very low link utilization for most of their links, and then a lot of the delays were caused by very few links. And in fact, Google's BBR algorithm is exactly trying to fix this very issue. And the third, and this was actually the main reason for DARPA's and ONR's interest in this work, was the issue of convergence, right? So from their point of view, you have mobiles that are moving, and the topology sort of keeps changing. So you want algorithms that converge very fast. From a commercial point of view, we are very much on the verge of the 4th industrial revolution that's been driven by the need to connect everything to everything. And this means that if you have algorithms that take some time to converge to a good solution, forget optimal, then those algorithms might not be very useful, because by the time they converge to a good solution, you've already changed the topology and you've changed the dynamics in the system. That's why you need algorithms that converge very, very fast. And so this calls for a systematic design. This is probably a very elementary chart for most of you, so I'll go through this quickly, all the way from the transport layer to the physical layer. And this is exactly what people have been looking at for a while now through the lens of cross-layer optimization, where the idea is that unlike this fellow who's looking at this problem very myopically, you want to look at the entire structure of the protocol stack in order to improve performance. The idea being that if you sort of increase the state space, you're going to get a more sort of optimal kind of solution. Right? Now, during the process of thinking about cross-layer optimization, there were some important attributes to consider. One was to make sure that you don't destroy this beautiful architecture that has been created and works for many, many years. So you want your functionalities to be coupled in a loose manner rather than in a very tightly coupled manner, as well as have an implementation that's scalable. And this is where network utility maximization comes into play, and this is something that we will re-examine for the purpose of this talk. So what is network utility maximization? So this structure provides the mathematical foundation, sort of, you can think of it as a unifying mathematical framework for jointly optimizing each of the functional components across the network stack. And the beauty of this algorithm, and I'll talk about this formulation, is that when you solve it, you have real protocols, real algorithms that pop out from the solution. But let me first just give you a high-level view of the overall problem. So here is the general mathematical model of network utility maximization. And just for notational simplicity, I'm going to focus right now on wireless networks. So the idea is that you want to choose the rate at which packets are injected into the network. So from a TCP point of view, you might think of, say, the window size, as well as the routing parameters, okay, in order to maximize the sum of the utilities, which depends on the rates that you support on the network. And traditionally, the utility functions are non-decreasing and convex. So the idea being that, non-decreasing and concave. So the idea being that if you get a small data rate X, that is bad, and having more is beneficial. And then after a certain point, the application really can't use much more. So there's a point of diminishing returns. Another reason why concavity is used is to ensure fairness. So it turns out that depending on this utility function, you can provide different types of fairness, from proportional fair to maximum fair. A whole host of fairness can be provided across the flows. And a flow here is simply an abstract construct which basically says, there's a source that's transmitting through a destination. It doesn't necessarily mean that it has to follow the same path through the network or anything like that. It's just the amount of data from source to destination. All right? And so the first constraint here is basically giving you the per node destination flow conservation law. And the second constraint is your link capacity constraint. Okay? And so let me illustrate these constraints in this toy problem. So here you have two sources that are transmitting to two destinations, source 1 to destination 1, source 2 to destination 2, and you want to maximize the utility of your data rate at source 1 and the sum of the utilities of the data rate at source 1 and source 2. So This is given by the objective function, and then the first constraint is the flow balance constraint at the ingress of this link, the bottleneck link, and the second is at the egress of the bottleneck link. And then these are simply capacity constraints, and just for simplicity, I've kept a uniform capacity constraint, but you don't need to. Each one, each of these links can have different rates and so on. So let's look at some of the existing solutions here and then some of the key challenges. So the nice thing about the solution of this problem is that there exists a very beautiful mathematical decomposition theory, which has been used as the foundation for solving this problem, typically through something called a dual Lagrangian dual and subgradient method. And the nice thing about this is that when you solve this problem, as I said before, an actual algorithm pops out. So you get a precise congestion control algorithm, a routing algorithm, routing scheduling algorithm, etc. And here are some key papers in the wireline area. Stephen Lowe had one of the first papers in this area. In the wireless context, where we have to also include interference, we had one of the first papers in this area as well. But there has been lots of parallel works here. Okay, so the basic idea is you write the problem as traditionally as a dual problem, although there are some primal solutions as well. And this Lagrangian dual function of this problem includes two parts. One is the objective function, and the second part is the penalty of the constraint violation. Okay. And you can think of this lambda as the dual variable, and oftentimes that basically corresponds to the physical Q length or the round trip time scaled by some constant. And if you do a flow by flow decomposition of this problem, out pops the congestion control solution. So here you can see that the congestion control problems determines the injection rate or the window size by solving a very simple one-dimensional optimization problem. Right? And the information required is only the Q length at the source. And as I said earlier, the specific form of the utility function can give us specific fairness requirements. So for example, Stephen Lowe has shown that, depending on the type of utility function, like if you use a weighted logarithmic utility function, you can actually emulate what TCP does in terms of providing fairness, etc. Now, if you do a link by link decomposition, you get a type of dynamic routing, which is well known. It's called backpressure routing. Once again, here what you do is you determine the service rate by solving a simple linear program, and the only information you require is your Q length and your neighbor's Q length. So you require this differential Q length backlog. And then you can do a Q length update, and once you do all of that, you solve the overall problem. So the advantage is that there is this beautiful, nice decomposition which allows this loose coupling, because the coupling is only through these Q lengths. Otherwise, it's like you're solving a transport layer problem, a routing problem, all of these separately, right? It's distributed, only one hop communications is required, at least in the wireline case. In the wireless, it's a little more complex, but you can make it distributed, and has low complexity. All very good things. So what are some of the issues with this? The big disadvantage of this approach is that it has slow convergence. So if you want to get to within epsilon of the optimal, the subgradient descent part of the algorithm requires an order 1 over epsilon number of iterations. So this takes a long time to converge. And then there is a latency utility optimality trade-off. So if you want to get to within, say, 1 over k of the optimal throughput, then it means your delay must increase on the order of k. Q length must increase. So, the question is, can we design more efficient algorithms? And there is indeed work that's gone on in this area. So one approach has been to use what are known as the second order methods. Typically, they use the Newton's method, which gives you much faster convergence speed. In fact, the convergence speed per iteration is very, very fast. But then each iteration turns out to be quite expensive. Okay, and it's not easy to decentralize. In fact, surprisingly, when you actually run this algorithm in practice on large networks, it performs quite poorly because each iteration is quite heavy. Moreover, the latency throughput trade-off is larger. So now if you want to get within 1 over k of the optimal, the delay grows as k squared. So to address some of these issues, and we ourselves had some follow-up work on this problem, and and even our works have similar problems. But we followed up with some other types of techniques that are used in machine learning, etc., and from classical optimization, called momentum-based acceleration, where you essentially add a weight which uses a little bit of history information. Like heavy ball, for example, uses, instead of having a purely index-based policies like the ones that we had before, you use essentially one more degree of information from the history. And empirically, you can substantially improve the convergence speed, also get better latency throughput trade-offs. Like, for example, if you get to 1 over k now, your delay is growing only a square root of k. But it's still growing, and that's an issue. So there is this other line of work which actually I had completely forgotten about, but we had developed some algorithm, not in this context, but for multipath routing in 2006. And when we looked at this algorithm, we found that, in fact, that particular algorithm, you can get to the capacity region without the Q length going to infinity. But here the issues was this was purely for a wireline network, and it was not developed for wireless networks. And recently there was an extension of this by UN Neely using a different technique. They also found a low latency throughput trade-off, where essentially you can get to the boundary of the capacity region with finite Q lengths. And they do show convergence speed, but they are able to show it only in an average sense. And it grows as 1 over epsilon, which means that as you get to epsilon of the optimal, your rate of convergence is growing on average as 1 over epsilon. And then I'll talk a little bit later about the different types of convergence rates that one can study. The other disadvantage of this is that it's not applicable to wireless networks. It only works for wireline networks. And so the key question is, can we do more? Can we do more on this, these three axes of convergence time, complexity, and delay? Can we design an algorithm that somehow simultaneously solves this big open problem to give you sort of, something which is very, very close to sort of, having as low delay and complexity and convergence as possible? And the answer is roughly yes. And that's what I'm hoping to show you, at least partially through this talk. So this summarizes our new result in relationship to the other works that have been developed. So this new method, which we call the inexact Uzawa ADMM method, you can see achieves the fastest convergence speed compared to the others, even faster than the distributed second order. It gives you optimal throughput, and even at the boundary of the capacity region, we get finite Q lengths. The routing complexity is almost the same as first order techniques. It basically has a logarithmic term extra. So there's there's that. And it also works for wireless as well as wire. The nice feature of this algorithm, it also has this beautiful mathematical decomposition structure that the original utility maximization algorithms had. It has a distributed dynamic routing component, a distributed congestion control component, and a queue-length update component. The key difference between the others is that you have a quadratic penalty function in both the routing and the congestion control pieces, and you're making decisions based on virtual queue lengths instead of the exact queue lengths. It works quite well. We've run this on a variety of different networks. Raytheon, ran very large-scale simulations with it, and it substantially improves on the existing state of the art. You can see that even when the networks are very, very large, the number of iterations and the queue lengths are much lower than what is with other techniques. Because the drift plus penalty approach that Neely has developed doesn't work for wireless networks, the performance is even bigger. So it seems like something that works well. So how does this design come to place? So let's look under the hood and find out how this algorithm was designed. So the main idea that we have is that we've solved this network utility maximization problem by modifying a particular technique used in convex optimization called the alternating directional method of multipliers. Okay, that's aimed to solve convex optimization problems, large ones, by breaking them up into smaller pieces. Yeah. And this technique, as I said, we call the inexact Uzawa ADMM method, and I'll explain why. So the first step is to reformulate the original network utility maximization method such that it works with an ADMM type of formulation. The second step is to apply a particular update rule, which is called the Gauss-Seidel ADMM, to get a three-step iteration algorithm. And here, one of the big challenges is that one of the primal update steps is non-decomposable, so applying a standard technique turns out doesn't quite work. And then we have to address this technique by developing an Uzawa method, which is a local second-order approximation, and then we show how to get exponential decay rate or global linear convergence rate. All right, so let's recall the original network utility maximization problem. And as I said, before we can even use ADMM, we need to reformulate it in the context of the ADMM as a two-block separable optimization problem. So let's do that. So what we'll do is we'll take one of these constraints and we'll move it to the objective function by defining a proper convex indicator function in the following way. So this moves essentially the constraint to a penalty, and we have an equivalent optimization problem. And then the second step is we write the node destination flow conservation law in a two-form separable way, which has this matrices B and A, where X is the vector of the injection rates, R is the vector of the service rates. And you can see what these matrices look like for the simple toy example, right? So you have these matrices that basically are neither diagonalizable or a square, but have a certain structure. And now you have this two-block separable optimization problem where one block essentially optimizes the injection rate, the other block optimizes the service rate, and then these two are coupled by a flow conservation. And so we are ready to first try out a standard ADMM approach, which is to essentially augment the Lagrangian function with a quadratic penalty. which is what we do. And when we do that, we get a 3 iteration steps of ADMM using this Gauss-Seidel update rule. So in the first update, we optimize the service rate. That's primal update 1. Then primal update 2 optimizes the injection rate. And then the dual update updates the virtual queue length. What is nice is that this primal update 2, the second primal update, can be decomposed in a very easy way. You can do a flow-by-flow decomposition, and you get a fully distributed congestion control algorithm, which looks complicated, but it's very similar to the one you had before. It determines the injection rate of the window size by solving a simple one-dimensional convex optimization problem. And the information required is simply the virtual queue length and the service rate in the adjacent link. So it's fairly distributed. The problem becomes when you want to solve the first primal update. And this is not easy to solve because it's non-decomposable. The matrix A is non-orthogonal. Okay? So if you look even at the toy example, you will see that A transpose A does not have a diagonal structure. And therefore, this is clearly not easily distributable. Okay, so our solution is to use a technique in the theoretical computer science literature called the Uzawa ADMM, where we essentially do a local second order approximation of this function. Okay, so this local second order approximation has a constant term with respect to the function, a linear term which is separable, and another diagonal term which is separable. And then if you do some algebraic manipulations, you get this dynamic routing component, which when you look at it, looks a little bit difficult to solve because it's a quadratic optimization problem for each link. But the good news is that you can actually solve this problem by some projection techniques in order f log f time, where f corresponds to the number of flows or source destination pairs in the network. And once again, you only require local information. Yeah? And after determining the service rate, you basically do a virtual queue length update and you're done. Okay? You can in fact show that if the utility function is proper concave, so it doesn't even have to be strictly concave for this part, the injection rate as well as the physical queue length satisfies these equations, which basically means that you have vanishing utility gap with finite queue lengths even at the edge of the capacity region, which is great. So which means you have low delays, as you saw in the simulations. Now, to show throughput optimality or to show that this particular result holds, you need to show something in the literature called proof of stability. Okay, so you want to show that the system is stable even at the edge of the capacity region. And the traditional first order methods that are used in the dual decomposition literature typically use what is known as a quadratic Lyapunov function to show stability. For those of you who've taken classes in control, you know what a Lyapunov function is, and what you want to show is that this Lyapunov function has negative drift and it doesn't work. I don't know how many control theorists are in the audience, but an element of constructing a Lyapunov function is an art as well as a science. And so in this particular case, the construction that we have has two components. It has a distance to the optima plus a constraint violation. And then we show that this function under our algorithm has negative drift. It's monotonically non-increasing. And this allows us to show that both the primal and dual variables converge to the optima. And then we can show that the physical queue length is actually bounded by the magnitude of the dual variable. So this allows us to basically show that the queue length is finite even when rho goes to 1. All right, so now let me talk a little bit about convergence rate. So before I do that, let me overview give you a little bit of an overview of the different convergence rates that are possible. I will, let's say that you have an algorithm that you're designing for this problem or any other problem, which spits out a value at each time t called x sub t. Okay, and let's say x star is the optimal solution. Then you can think of a sub t, which is the difference of x sub t and this optimal value, is the error at each point in time. Okay, so this is your error sequence. So global linear convergence simply says that at each time step t, and at every time step t, that's the critical part, okay, this value is actually decreasing geometrically. So the magnitude of your error is going down exponentially, or in the case because it's discrete, so it's geometric. Okay, where you can see alpha is between 0 and 1. And so in this case, the number of iterations tends to be very low in order to show, for convergence. If you want to get to within epsilon, you only need log 1 over epsilon. And global simply means that this happens for every t. If we didn't have global here, it would base, you would just say showing linear convergence basically would say that there is a large enough t after which this happens. Okay? So global is simply a stricter form of it. And then global sublinear convergence means, for example, that the error decays, as 1 over t, or error decays as square root of t. So in this case, for example, the number of iterations would be larger. You'd have order 1 over epsilon, or it could be even much larger, 1 over epsilon squared, like you had in the traditional dual decomposition approaches. And then ergodic convergence simply means that you are not really dealing with the actual convergence, but you're dealing with the average convergence. And so this is weaker than the non-ergodic case, and you can replace it for any of them. And that's what's shown for the drift plus penalty function that Neely and all had developed. So can we get global linear convergence is the big question here. Can we get this exponential decay of the error? So it turns out that in the theoretical computer science literature, there is some existing analysis that has established a rate of convergence of 1 over epsilon of this Uzawa ADMM technique that we developed for this problem here. And this can be shown under the objective function being concave. Okay? The question is, because it's too slow for what we need, can we do better when you have strict concavity, which is what you have with most utility functions that we use in networking systems? In fact, even very general utility functions like the ones in Moe and Walron's paper are all strictly concave. And it turns out that we are able to exploit the curvature of this of this utility function, and in fact get a better convergence rate. So how do we do that? So recall that our Lyapunov function had this descent inequality. So we showed that it was, had non-decreasing kind of rate. Now, if you can show that this Lyapunov function times a constant is less than or equal to the right-hand side, then you're done. Why? Because you can move this constant, to the denominator, and so you can see exponential delay. And because the Lyapunov function, one of the term is the distance to the optima, it ensures that at every step you're decreasing that distance in this geometric or exponential way. Now, if you can do this, you're done. And in fact, again, in the theoretical computer science literature, there has been some work that has established this above inequality when both matrices A and B are full rank. Full column rank and full row rank. So the question is this the case for us? If so, we are done. Turns out that even for the toy example, this is not the case. Neither the node arc incidence matrix A nor this matrix B is a full rank matrix. And so this is actually the key technical challenge of this work, and we needed to find a completely new technical path that exploits the structure of the problem in order to show a global linear convergence. In fact, we show that if the utility function is strictly concave, the injection rate and service rate produced by the new algorithms converge globally and linearly, as you can see by these equations. Okay? All right, so let's spend some time discussing some of the issues with this. So the first thing is, let's make a connection to this very nice algorithm that was developed for wireline networks by you and Neely, which is this drift plus penalty algorithm. So if you recall, our Gauss-Seidel ADMM had this 3 steps. And we had to essentially decompose the first step using this Uzawa method. And the question is, can we apply this technique to another type of an update rule called the Jacobian update rule, which will make a connection to Neely's approach. So if you look at the Jacobian type of rule, the update rule is exactly the same as the Gauss-Seidel, except that it's making a decision based on a previous time swap, okay, the primal update 2. And in fact, you can show that if you decompose the first step by adding this quadratic regularizer like we did for our algorithm, it recovers under some specific parameters the exact algorithm that you and Neely have developed. And then using our proof techniques, we can actually immediately show an improved convergence rate over what they have. So instead of order 1 over epsilon, we can show little o of 1 over epsilon. And moreover, ours is not an average convergence rate. It's actually the non-ergodic convergence rate. Okay? So in fact, that's one of the reasons why the Neely's algorithm works quite well. It doesn't quite give you global linear convergence, but it's still giving you pretty good convergence. But it works only in the wireline case. Okay, now the question is, we've talked about the wireline case. Can we extend it to the case where we have interference in the network? And it turns out that we can. The congestion control and the Q-length update remain virtually the same. The routing component that we had, this backpressure routing, now includes both routing, this quadratic routing, now includes both routing and scheduling. And so the way you do this is you essentially use the same sort of a notion of a capacity region in the wireless case, where essentially you can think of pi being the set of link powers. Then depending on the coding scheme, you would get G, which is the rate power vector. And so you can think of lambda as being the set of feasible rate vectors. And so the capacity region would be the sum rate of each at each link, which is an element of the convex hull of this set of feasible rate vectors. The convex hull being that you are allowing for time interleaving. So you're allowing for one set of nodes to shut up while the other set of nodes are transmitting. And so the question is, how do you solve the new routing scheduling problem? This is quite complex. I don't have time to get into it, but basically we have an equivalence theorem, which basically says that if you have a solution in the traditional first in the traditional network utility maximization, which uses something called max weight scheduling, which is NP hard, then you'll get an NP hard solution in our case. If it's polynomial, then you'll get polynomial time solvable in our case as well. So you essentially have this equivalence theorem. So we can come up with a similar technique. So for example, if you can come up with an approximation of this, we should be able to come up with an approximation as well. And for the node exclusive model, which essentially corresponds to a model in which nodes cannot transmit and receive at the same time. So you have like this one hop interference model. we can show that the complexity of the algorithm is polynomial, but quite high. It's got n to the 5, where n corresponds to the number of nodes in the network. So that's higher than the max weight scheduler in traditional systems, which has order n cubed. So we propose a new solution, which uses a modified version of an algorithm that's used in machine learning called the inexact Frank-Wolf algorithm, which essentially does is that at each time slot t has a number of iterations that it runs, and in each iteration it roughly gets a fraction of the optimal algorithm. So it's much simpler to solve that problem to get a fraction of the optimal, and it runs several iterations. And I won't bore you with the details, but basically you can show that you can get order n squared complexity for this. And in fact, this this type of a greedy algorithm works quite well. If you look at the simulations, you can see that even compared to the max weight algorithm, which is sort of throughput optimal, you get substantial reduction in delays in the queue length. And this is one of the reasons why, for the wireless case as well, the solution works quite naturally. So, high-level conclusion: we've successfully designed a distributed network control algorithm that simultaneously achieves good convergence performance, low delay, and low complexity. From a theoretical point of view, this is the first work to show global linear convergence of the inexact Uzawa method without any specific rank conditions. From a practical point of view, this algorithm has been implemented on a variety of large-scale simulations. Raytheon has implemented it. We've also implemented it on this Eminent core test bed, and it seems to be quite promising in terms of its performance. But there are many open questions. Okay, so the first one is that so far our algorithm assumes that everything is controllable and you don't have a fading in the system. Okay, so the question is, what happens when you have fading in the system? So the algorithm can handle wireless by getting interference, but can we sort of develop some tools that can rigorously handle fading? So we can do sort of heuristic things that handle fading, but we don't know what the convergence rate will be. We don't know what the utility delay trade-off will be in a rigorous sense. So that's a big question, right? Another question is, now what happens when you have inelastic traffic, which is where traffic that's not controllable in the network, and you can only control one class of traffic? How do you coexist? And there we've done some work in the traditional setting with load balancing, etc., in order to kind of get some nice results. And the question is, can that be done in this context as well? In the traditional setting, in the wireless setting, a lot of these scheduling mechanisms like max weight, etc., are too heavy to implement. And so people have implemented them through these randomized algorithms. So there are these queue length based CSMA algorithms that have been used very effectively. And the question is, can we incorporate them with this Uzawa ADMM? This is something which I'm trying to get a student to work on, because Sinong graduated, so we have a little bit of a gap. The final question is that, Stephen Lowe, for example, started a company where he used the network utility maximization to come up with, this TCP fast and so on, by modifying, the active queue management mechanisms. Again, the question is, can we do the same with the ADMM based frame? And this is where I will stop and take questions. Thank you.
Okay, thank you, Dr. Shroff. for the great talk. I guess, yeah, we have one question right now from Edward. So the question is, do you envision that deployment within data centers would realize most of the benefits, or does the approach need end-to-end deployment?
No, certainly you can. I mean, you can get quite a bit of the benefit within a data center itself, and you know, you don't need you don't need to sort of do it across the entire internet, for example, to get the benefits.
Yeah, I was thinking that within a data center, you get the ability to really just do a complete clean slate design and just turn the switch.
Mm-hmm.
And so I'm just, maybe to rephrase it a little bit, are the latency convergence issues that you pointed to when you started,
Right.
Are those problems in the data center, or those problems are somewhere else out in the backbone? So where should this be deployed first? Maybe that's another way to
yeah. So in fact, I would definitely start by implementing it in the data center itself, because as you pointed out, you have much more control of implementing the algorithms within the data center, and you can, in a certain sense, utilize the full power of the technique there. If you start to go, end to end, then you need to sort of, figure out how to accommodate, for example, making it TCP compliant and so on and so forth, which will certainly reduce some of the benefits of the algorithm.
Okay.
So you'll be able to control the rate a little less precisely, because you're doing things to make sure that you are TCP compliant.
Thanks.
So I guess Ashu also wants to ask a question.
Go ahead, Ashu.
Wireless and then extension to fading. Could you comment on what kind of information do you need to actually operate the algorithm? Is it the channel information, link quality information?
Yeah. So if you can get the SINR information, that would allow you to operate the algorithm.
And is that one hop, or is it across multiple hops?
So if you want the absolute optimal, then it would have to be across hops. But as you saw with the greedy algorithm, which could be very readily distributed, you only need one hop type of information.
I see. Now, could you also comment on, like in this scenario, some notion of robustness to error in knowledge? Like is the function smooth enough so that you actually end up with small errors leads to small errors in the way the optimum?
Yeah, so I mean, I'll be very honest, I haven't done this analysis for this work, but the original network utility maximization work, we have a paper called Impact of Imperfect Scheduling. And there it was quite robust to the errors. I suspect that it should be quite robust here as well, in the way, because of the way in which the operation happens. In fact, here oftentimes you're not doing time interleaving. You are actually transmitting, to multiple, you're transmitting a little bit of rate to sort of multiple nodes. And so I would expect that, in fact, the error should have, even perhaps potentially less impact. But I'm not sure, to be honest. I haven't.
And then one more, just kind of considering how the model which you presented generalizes. Perhaps it's very straightforward, or maybe needs a little work on. Then in wireless, now there is multi-user systems which you can communicate simultaneously. Is that it naturally fits into the graph model you have, the network model?
Yes. Certainly, as I said, I mean, everything that we were able to fit into the traditional system should fit here from an algorithmic point of view. However, I would have to still, yeah, I don't have a good answer for you, whether we can come up with the same type of proof results.
Okay. All right.
Yeah.
Thank you.
Sure.
Okay. I guess I can also ask a question. So I was wondering,
Sure.
follow up to Ashu's, like for example, for cellular networks, what are the ramifications for cellular networks, and how can be we have a mix of wired and wireless links?
That should not be a problem. I mean, so you can think of cellular networks as being sort of one-hop communication, right? So there it would be sort of, interference is the big bottleneck, right? So it should be, I mean, what I mean by that is that from the point of view of designing a good scheduling algorithm, you need to worry about interference. So cellular networks should work, but of course, all of the problems that you have in the traditional, optimal scheduling algorithms. For example, we know that for general interference model, the optimal scheduling algorithms become NP hard, even if you have one-hop transmission and interference. And that would be the same thing here. So you would have to come up with sort of, efficient, randomized algorithms that can get you provably efficient performance. Again, as you do in the standard approaches.
I see. Okay. So I guess that was all with the questions. I would like to thank you again, Ness, for joining us today. It was a great pleasure to have you. I hope we can actually have you in person in the near future if the situation permits. But that was great today, and I would like to thank everyone else for joining us today.
Thank you very much, everyone. It was a pleasure. We'll chat later.